New Horizons design and construction. Spacecraft subsystems. The spacecraft is comparable in size and general shape to a grand piano and has been compared to a piano glued to a cocktail bar-sized satellite dish. As a point of departure, the team took inspiration from the Ulysses spacecraft, which also carried a radioisotope thermoelectric generator, RTG, and dish-on-a-box-in-box structure through the outer solar system. Many subsystems and components had flight heritage from APL's Contour spacecraft, which in turn had heritage from APL's Time spacecraft. New Horizons body forms a triangle, almost 0.76 meters, 2.5 feet, thick. The Pioneers have hexagonal bodies, whereas the Voyagers, Galileo, and Cassini-Huygens have decagonal, hollow bodies. A 7075 aluminium alloy tube forms the main structural column, between the launch vehicle adapter ring at the rear, and the 2.1 meters, 6 feet 11 in, radio dish antenna fixed to the front flat side. The titanium fuel tank is in this tube. The RTG attaches with a four-sided titanium mount resembling a gray pyramid or step stool. Titanium provides strength and thermal isolation. The rest of the triangle is primarily sandwich panels of thin aluminium face sheet, less than 1/64 in or 0.40 mm, bonded to aluminium honeycomb core. The structure is larger than strictly necessary, with empty space inside. The structure is designed to act as shielding, reducing electronics errors caused by radiation from the RTG. Also, the mass distribution required for a spinning spacecraft demands a wider triangle. The interior structure is painted black to equalize temperature by radiative heat transfer. Overall, the spacecraft is thoroughly blanketed to retain heat. Unlike the Pioneers and Voyagers, the radio dish is also enclosed in blankets that extend to the body. The heat from the RTG adds warmth to the spacecraft while it is in the outer solar system. While in the inner solar system, the spacecraft must prevent overheating, hence electronic activity is limited, power is diverted to shunts with attached radiators, and louvers are open to radiate excess heat. While the spacecraft is cruising inactively in the cold outer solar system, the louvers are closed, and the shunt regulator reroutes power to electric heaters. Propulsion and attitude control. New Horizons has both spin-stabilized, cruise, and 3-axis stabilized, science, modes controlled entirely with hydrazine monopropellant. Additional post-launch delta V of over 290 meters per second, 1,000 kilometers per hour, 650 miles per hour, is provided by a 77 kilograms, 170 pounds, internal tank. Helium is used as a pressurant, with an elastomeric diaphragm assisting expulsion. The spacecraft's on-orbit mass including fuel is over 470 kilograms, 1,040 pounds, on the Jupiter flyby trajectory, but would have been only 445 kilograms, 981 pounds, for the backup direct flight option to Pluto. Significantly, had the backup option been taken, this would have meant less fuel for later Kuiper belt operations. There are 16 thrusters on New Horizons, 4.4 N, 1.0 lbf, and 12 0.9 N, 0.2 lbf, plumbed into redundant branches. The larger thrusters are used primarily for trajectory corrections, and the small ones, previously used on Cassini and the Voyager spacecraft, are used primarily for attitude control and spin-up/spin-down maneuvers. 2 star cameras are used to measure the spacecraft attitude. They are mounted on the face of the spacecraft and provide attitude information while in spin-stabilized or 3-axis mode. In between the time of star camera readings, spacecraft orientation is provided by dual redundant miniature inertial measurement units. Each unit contains 3 solid-state gyroscopes and 3 accelerometers. 2 ADCOL sun sensors provide attitude determination. One detects the angle to the sun, whereas the other measures spin rate and clocking. Power. A cylindrical radioisotope thermoelectric generator, RTG, protrudes in the plane of the triangle from one vertex of the triangle. The RTG provided 245.7 W of power at launch, and was predicted to drop approximately 5% every 4 years, decaying to 200 W by the time of its encounter with the Plutonian system in 2015 and will decay too far to power the transmitters in the 2030s. There are no onboard batteries since RTG output is predictable, and load transients are handled by a capacitor bank and fast circuit breakers. The RTG, model GPHS-RTG, was originally a spare from the Cassini mission. The RTG contains 9.75 kilograms, 21.5 pounds, of plutonium-238 oxide pellets. Each pellet is clad in iridium, then encased in a graphite shell. It was developed by the U.S. Department of Energy at the Materials and Fuels Complex, a part of the Idaho National Laboratory. The original RTG design called for 10.9 kilograms, 24 pounds, of plutonium, but a unit less powerful than the original design goal was produced because of delays at the United States Department of Energy, including security activities, that delayed plutonium production. The mission parameters and observation sequence had to be modified for the reduced wattage. Still, not all instruments can operate simultaneously. The Department of Energy transferred the space battery program from Ohio to Argonne in 2002 because of security concerns. The amount of radioactive plutonium in the RTG is about one-third the amount on board the Cassini-Huygens probe when it launched in 1997. That Cassini launch was protested by some. The United States Department of Energy estimated the chances of a New Horizons launch accident that would release radiation into the atmosphere at 1 in 350, and monitored the launch as it always does when RTGs are involved. It was estimated that a worst-case scenario of total dispersal of onboard plutonium would spread the equivalent radiation of 80% the average annual dosage in North America from background radiation over an area with a radius of 105 kilometers, 65 miles. Flight computer. The spacecraft carries two computer systems, the command and data handling system and a guidance and control processor. Each of the two systems is duplicated for redundancy, for a total of 4 computers. The processor used for its flight computers is the Mongoose V, a 12 MHz radiation-hardened version of the MIPS R3000 CPU. Multiple redundant clocks and timing routines are implemented in hardware and software to help prevent faults and downtime. To conserve heat and mass, spacecraft and instrument electronics are housed together in EMs, integrated electronics modules. There are 2 redundant EMs. Including other functions such as instrument and radio electronics, each EM contains 9 boards. The software of the probe runs on Nucleus Vertos operating system. There have been 2 safing events that sent the spacecraft into safe mode. On March 19, 2007, the command and data handling computer experienced an uncorrectable memory error and rebooted itself, causing the spacecraft to go into safe mode. The craft fully recovered within 2 days, with some data loss on Jupiter's magnetotail. No impact on the subsequent mission was expected. On July 4, 2015, there was a CPU safing event caused by overassignment of commanded science operations on the craft's approach to Pluto. Fortunately, the craft was able to recover within 2 days without major impacts on its mission. Telecommunications and data handling. Communication with the spacecraft is via X-band. The craft had a communication rate of 38 kilobits per second at Jupiter. At Pluto's distance, a rate of approximately 1 kilobit per second per transmitter was expected. Besides the low data rate, Pluto's distance also causes a latency of about 4.5 hours, one way. The 70 meters, 230 feet, NASA Deep Space Network, DSN, dishes are used to relay commands once it is beyond Jupiter. The spacecraft uses dual modular redundancy transmitters and receivers, and either right or left-hand circular polarization. The downlink signal is amplified by dual redundant 12-watt traveling wave tube amplifiers, TWTAs, mounted on the body under the dish. The receivers are new, low-power designs. The system can be controlled to power both TWTAs at the same time, and transmit a dual polarized downlink signal to the DSN that nearly doubles the downlink rate. DSN tests early in the mission with this dual polarization combining technique were successful, and the capability is now considered operational, when the spacecraft power budget permits both TWTAs to be powered. In addition to the high-gain antenna, there are 2 backup low-gain antennas and a medium-gain dish. The high-gain dish has a Cassegrain reflector layout, composite construction, of 2.1 meter, 7 feet, diameter providing over 42 dB of gain and a half power beam width of about a degree. The prime focus medium gain antenna, with a 0.3 meter, 1 foot, aperture and 10 degrees half power beam width, is mounted to the back of the high gain antenna's secondary reflector. The forward low gain antenna is stacked atop the feet of the medium gain antenna. The aft low gain antenna is mounted within the launch adapter at the rear of the spacecraft. This antenna was used only for early mission phases near Earth, just after launch, and for emergencies if the spacecraft had lost attitude control. New Horizons recorded scientific instrument data to its solid-state memory buffer at each encounter, then transmitted the data to Earth. Data storage is done on 2 low-power solid-state recorders, one primary, one backup, holding up to 8 GB each. Because of the extreme distance from Pluto and the Kuiper belt, only one buffer load at those encounters can be saved. This is because New Horizons would require approximately 16 months after leaving the vicinity of Pluto to transmit the buffer load back to Earth. At Pluto's distance, radio signals from the space probe back to Earth took 4 hours and 25 minutes to traverse 4.7 billion kilometers of space. Part of the reason for the delay between the gathering of and transmission of data is that all of the New Horizons instrumentation is body-mounted. In order for the cameras to record data, the entire probe must turn, and the 1-degree wide beam of the high-gain antenna was not pointing toward Earth. Previous spacecraft, such as the Voyager program probes, had a rotatable instrumentation platform, a scan platform, that could take measurements from virtually any angle without losing radio contact with Earth. New Horizons was mechanically simplified to save weight, shorten the schedule, and improve reliability during its 15-year lifetime. The Voyager 2 scan platform jammed at Saturn, and the demands of long-time exposures at outer planets led to a change of plans such that the entire probe was rotated to make photos at Uranus and Neptune, similar to how New Horizons rotated.